Hello, everyone. We are here again for the Hackers Cup webinars. Today we are with Joe. Joe works from the torchtune team at Meta. He has been developing this awesome library that lets you fine tune your models, bring your own data, and it's very streamlined. If you haven't checked it out, it's probably worth checking it out. It's simpler and has like a full training loop that you can access and easy to hack and modify. So, hello, Joe.
Hey Thomas, thanks for having me. Yeah, no, I was watching a bunch of the other videos for this Hacker Cup lecture, and it's a ton of cool stuff. But I'm excited to talk about some of the open model weights and open track, 'cause I think that's been missing a little bit.
Yeah, I feel that this is not the first talk, but this is very targeted at the open track that needs to fine tune something.
Mhm.
Like, of course, that track has two parts, like creating the data set where you're going to fine tune. And I think
Yeah,
that's not counted on the 24-hour A100. You can bring your data set, just make it public.
yeah,
And then you have like 24 hours of one A100 with 40 gigs. It's not the big one to fine tune the best possible model. Try to solve as many problems as you can and submit your solutions. So like it's like a multi-stage and it's a complex pipeline. So
yeah.
yeah,
The
thank you for being here. Like this is probably the most useful starting point for people that are gonna like tackle that track.
yeah, the 40 gigs VRAM is sadistic. There's so many cool models, and they won't either quantize down or fit in that amount of space, but we'll make it work.
But we have efficient fine tuning and all the tricks out there and low,
Yeah,
yeah, mixed precision and quantization.
yeah,
So
lots of it.
let's go, Joe. I give you the floor and
All
let's get
right,
started.
let me share my screen. All right. All right. Yeah, like Thomas said, you know, I'm from the torchtune team. As part of PyTorch, we've been working on this for several months now. But I'm sort of going to take a more broad approach, just about fine tuning in general. There's lots of great tools out there, and torchtune is just one of them. So here we go. Um, yeah, this is sort of going back through and watching the the other presentations that we sort of had. There's this notion of we take an elite code question, it goes into our AI system, whatever that is, and we have code as the output. And I think either you or Mark said it in the first thing. It's not just going to be that you have zero shot to some model weights and then it perfectly outputs some code. It's going to be calling from one model to another, maybe some sort of filtering that, all right, does this actually pass a linter or something like that, or does this take in the input and provide the correct output for the sample inputs. But at the core of that, there are some model weights, and so to sort of like push back on that is that, we gotta figure out how to like have the very best model, um, to sort of answer some of these questions. uh, and so if we look at this is a screenshot from the chatbot arena, which is a tool that essentially like lets people chat between two different models, and sort of uprank one if it's better, downrank one if it's not better or worse than the other one, and you sort of get this sort of like stack ranking. Um, and I really like these because it captures all of the models are going to be releasing their uh, you know here's how I did on XYZ task like MMLU. But that doesn't actually give you a feel of how well the model is performing. So Chatbot Arena, for the most part, it has its issues, but for the most part, will give you a sort of good understanding of how these stack rank against each other. But I wanted to sort of point this out that if you look at the screenshot from a couple days ago, uh, there's only two models here that are non-proprietary. And these two models are Mistral Large and the Llama 3.1 405B. And so if I'm looking at this open track in which I have to have a completely reproducible fine tuning run and inference run using one of these open models, uh, I feel very disappointed looking at this. I feel like I have, I'm open track, obviously we're not stack ranking open track against closed track, but I want to have the best sort of performance that I possibly can. And so it really makes me ask, like, is open track destined to always perform worse than closed track? And it's a very simplified question. There's lots of graphs that will tell you that open track is closing the gap on the closed models, which is definitely true. But for this competition in particular, the sort of like secret tool is fine tuning, of course. You take this pre-trained large language model, you add some custom knowledge base, and boom, you sort of have this domain or task adapted large language model. And in this case, we want to take a whatever model, like the best model we possibly can, train it on likely some code or some logic. There's some really great resources that you guys put out. And then our sort of end result there is the best possible coding model that we could possibly have. So yeah, the brief aside, like I said, I work for torchtune. It's a really awesome library. I feel obligated to briefly talk about it. Some of the things that we sort of hold as our design principles is just simplicity and extensibility. Everything is native PyTorch. Sort of like Thomas said, we have this notion of recipes and components, so you can reuse the components. We encourage you to copy and paste and modify the recipes as much as you want. It has a very exposed training loop, which Thomas and I were just talking before this. Fine tuning is as a formulated task is pretty simple. We're doing next token prediction, and so if you have access to that training loop that's doing something pretty simple, you can get clever. You can start using like gradient accumulation to reduce the actual batch sizes that you're holding in memory. You might be able to do a sort of I think Thomas, you were mentioning that there's if a loss explodes for whatever reason, it happens frequently, much more frequently in pre-training perhaps, but still sometimes in fine tuning, you can easily write a line of code there that checks the loss, sees if it's much higher than some sort of average, and then decide not to do the back propagation there. The other thing is correctness. There's a lot of the models are doing really clever things with their components. There's a million flavors of rope embeddings now. So making sure, obviously, that we're providing the most correct components and recipes. Stability, PyTorch and likes to just work, and so should torchtune. This is something that's not always taken for granted. The AI community and especially the LLM community recently, moves so fast that lots of stuff can kind of just break, and we're no exception to that, but we do our best to like make sure that we have really great testing, so that our users aren't frustrated by just startup issues. And yeah, the last sort of point there is, a lot of, you know, you could throw hardware at the problem. That's always a good solution. Sort of the scaling papers show that works great. But not everyone has access to, 1,000 H100s, unsurprisingly. So making sure that it works on whatever hardware you have, whether it be down to 16 gigabytes, up to more common like 48 gigs, like A6000 or something like that. All right, that overview sort of done. There's a lot of other great libraries that I absolutely want to mention. Axolotl, Wing is the creator of Axolotl and does some great work. And then also like Hugging Face has a trainer that you can sort of pick up and train models as well. I encourage you guys to look at all of them. But yeah, so I go back to this sort of chart here, and I have a problem at hand, which I want to uh, fine tune on some data and get the best possible model I can. I'm looking at this chart here, and in general, it looks like MetaLlama 3.145B is the best possible model. So I'm going to take that, I'm going to fine tune it, and I'm going to have the best model. I'm going to win OpenTrack, thousands of dollars, fame, glory, and it's going to be amazing. Unfortunately, as Thomas was mentioning, we have 40 gigabytes of VRAM, which is not nearly enough for 405B. Doing some quick math, there's about 2 bytes per parameter in the standard bfloat 16 that these models typically come in. So we're looking at about 800 gigabytes. And so normally, if I were to look at this problem, I would say, great, let's throw more machines at it. And so we have this very basic diagram that I drew in PowerPoint. We take 405B, we split it up into roughly 23 billion parameters per GPU. 16 GPUs. We call it a day. And we've just discovered model sharding. Unfortunately, again, we can't do this because we have access to a single A100 40 gigabytes VRAM. I hope it's coming across that I'm a little salty about this restriction because there's so many cool models that just simply won't fit. But there's also some really great talks about model sharding. Actually, Mark Seraphim, who's one of the people who's usually on this sort of talk, gave one with Jane Xu called Slaying OOMs. There's a link here. And then just more on general model sharding, some resources here as well. Really cool stuff, out of scope for this, unfortunately. So we have to ask the question, what the hell will fit in 40 gigabytes of VRAM? And when I'm sort of starting this problem, there's 2 big things that I can take a look at. And this is just what's going to fit to start my training. And the first is my model parameters. So what's the size of the model? And the second is what optimizer am I using? So, we have, let's just pick Llama 2, 7 billion. 7 billion, like I said, in bfloat 16, around 2 bytes per parameter, got about 14 gigabytes. And then for our optimizer, the most common one, and I, anecdotally, it seems like it just does the best. Some papers do study trying out different optimizers, but for the most part, people just take Atom W and run. But Atom W takes 4 bytes per parameter because it's storing some extra stuff like momentum, velocity. And so you've got about 28 gigabytes there. 28 plus 14 is over our 40 gigabyte limit. So even with something that I think people would consider a very basic model, 7 billion parameters, it's a pretty common size, usually one of the smallest you can get. We can't even start training because it's not going to fit in our 40 gigabytes of VRAM. And so we see the dreaded error there, which this is obviously looking at PyTorch, but it's the worst site that you could possibly see. CUDA out of memory, and then it gives you a bunch of stats like, oh, just how close were you to getting out of memory, which I always feel is very taunting. So I pointed out those 2 levers, model parameters and optimizers, and so arbitrarily, I would say, let's try to make this fit. Let's attack model size first. And so the sort of next smallest down that I was thinking of off the top of my head was Gemma 2 billion. So we have 2 billion parameters. Uh, Around 4 GB is the back of the envelope math. We can still use AtomW. We get to 8 GB, 12 total. We're well within our memory required for 40 GB, and so great. We can train. The issue is here that if we look at Gemma 2 billion versus Llama 2 7 billion, obviously, looking at one benchmark here, MMLU, which is a comprehensive set of tasks, you see that the larger model tends to do better, and this sort of comes to like the 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 rule that people follow is bigger models tend to perform better. Uh, there's lots of exceptions. I call out the QN2 team because they just put out a 0.5 billion model and a 1.5 billion model that are really amazing. And there's lots of other teams that are working hard in this sort of area. But going back to also our very first LMSys, chatbot arena thing, the best open source model was 405 billion parameters. So it's a rule of thumb. Bigger models tend to perform better. So therefore, we want to fit the biggest model that we possibly can uh, in our GPU. And so we have that other lever. We can attack the optimizer. Um, so AtomW is a pretty costly optimizer in terms of memory. So we can revisit things like stochastic gradient descent, our favorite friend from the very early days of machine learning. We can add momentum, so we can sort of store a little bit of extra information per parameter to sort of converge faster. Or we can try really, really fancy things like low precision optimizers. So instead of storing AtomW in 16 bits, we store in 8 bits. So we quantize down, we unquantize for the actual calculation, requantize, and we sort of get an approximation of the performance, but with half of the memory cost. So you see here that all of these are going to fit. Some have a little bit more headroom than others. But if I'm looking at this, if I'm thinking about if I want to really maximize the amount of space I have, stochastic gradient descent looks great. And in torchtune, it's as easy. We use a config system to sort of make ease of experimentation really easy. Pretty easy to pull from whatever library you want. So in the second one, I'm disappointed that Mark Serafim isn't here because I know he worked really hard on a lot of these low bit optimizers. So I can pull from Torch.io. I can pull from Bits and Bytes, which also does low bit optimizers. Or I can just pull from regular torch package, which takes has like stochastic gradient descent, AtomW, all of them. But again, looking back at this chart here, stochastic gradient descent looks great, but then we come to actually examining the runs, and we see here at the greenish bluish line, 100 steps and stochastic gradient descent is not really converging. You compare that to stochastic gradient descent with momentum, which converges slower, and then versus our 8-bit atom, which converges kind of like you would expect a normal sort of fine-tuning run to look. So turns out, the momentum and velocity of atom are extremely helpful to helping your model converge. And so having this sort of trick where we can quantize it down, save memory, is super valuable, and we should probably go with that. Brief aside, these last graphs obviously logged to weights and biases. Actually, some awesome work from Thomas. He put together a little guide for how to log to weights and biases in torchtune. And again, it's super easy to just sort of swap out the components in the config, give it a new project name, give it a new run name, And then you get some pretty graphs that are super helpful to determining whether or not your training is going in the right direction. So yeah, we talked about models, we talked about optimizers, uh, you know, bigger model better, general rule. So we're going to go with Llama 2 7 billion. But in order to make that fit, we need to either use the stochastic gradient descent, stochastic gradient descent with momentum, or 8-bit Atom W. We see in our previous experiments that 8-bit Atom W is appears to converge the quickest. So we have our biggish model, we have our optimizer. The only solution here is to profit immensely, win the competition, fame and glory. Everything is coming up aces. Unfortunately, we oom. And so we might be asking at this point, what the hell is happening? And that's I lied. I lied a little bit. These are the very first components that I like to consider because it's the blocker to getting something loaded into VRAM. But this is absolutely not the big picture. There are other things that we have not considered. Things like activations and gradients. And again, in my crude little drawing, we see that these do not quite fit in our 40 gigabytes of VRAM. To quickly talk about it, I think these are terms most people are probably somewhat familiar with. The gradient memory, gradient saved for each weight during training, so it's roughly equivalent to the number of parameters. An activation memory, these intermediate tensors that you get from forward calls. It's helpful to think of them in proportion to larger input sequence lengths or large batch sizes. They tend to be the bottleneck. And a lot of this information is actually from another talk that Mark gave, talking about why won't Llama 13B fit on my 4090. Quickly talking about, so we have these two new issues that have popped up. And we need another plan of attack to get these to work. And so in our last run, off the bat, we were using just a pretty normal batch size of 4. And so what we're going to do instead is use a batch size of 1 with a gradient accumulation of 4. So I think this diagram does like a decent job. So gradients are sort of how we tell the model which direction to go in, how to modify the weights in order that we learn better. I know that's a hand wavy explanation, but usually this is calculated at each step level, and so a large batch size increases the diversity of the data that your model is seeing. The gradients don't overfit to anything in particular on a certain step, but what we can also do is we can simulate a batch size of 4 with something called gradient accumulation, where instead of on every step we on every pass of every forward pass, instead of calling the optimizer and backwards, we accumulate the gradients for 4 steps, and then we do an update to the model, and sort of that way we get the sort of simulation of a batch size of 4 without holding the activations necessary for a batch size of 4, which is 4 times larger than what we would want. So we have gradient accumulation, pretty easy to enable in torchtune. And we see here that taking a look at another weights and biases log with Llama and 8-bit Atom, we are just under the sort of 40 gigabytes limits here, and still decent tokens per second. So we pulled on this lever and things seem to be training. But that's not the only sort of weapon that we have. We can also use activation checkpointing. So for each sort of forward path, we have these activations at our intermediate tensors, and instead of keeping them alive, uh, you know, we sort of omit saving these tensors and we recompute them during the backwards pass. So we're not taking the sort of memory hit right in the middle. So batch size of 4 doesn't work. Batch size of 4 with activation checkpointing works. And I think the natural sort of question here would be, this quick line here recomputes them during the backward pass. So there is a sort of performance hit, which is the case with most of like the memory sort of tricks we're doing to get things to fit. Is that more often than not, it's a trade-off between memory and performance. So if you want things to go fast, you load in a model in bfloat16, you use Atom, you don't need activation checkpointing, you don't do gradient accumulation, things just go super quickly. But once you start trying to work back the memory that you're using, it can take a performance hit, and that's important to know. Sort of in torchtune, it's one little line to enable activation checkpointing. And you see here that also, the peak memory allocated is below 40, and we've successfully done it. So putting it all together, if we were really concerned with the amount of memory we're using, we can use activation checkpointing and gradient accumulation together. Works fine. So yeah, this was sort of toy example. There's lots of other things that actually go into the memory, but those were the 4 biggest ones: model, optimizer, states, activations, and gradients. But this was, like I said, it's a toy example. All of these training runs were done on the alpaca dataset, which 99% of the samples are less than 1,000 length, and it actually has roughly like a 2,000 max sample length, which I don't think is accurate for code itself. For fine tuning on code for trying to understand a large complex piece of information that takes a lot more tokens. So instead of alpaca dataset, let's take a look at the evil code alpaca dataset, which is one of the datasets that I think was recommended by the Hacker Cup team as one to take a look at. So 90% of the samples are less than now 4K sample length, but there's a 33,000 max sample length. And so this is a much more realistic understanding of the kind of data that you might be seeing if you're going to fine tune your model to be an expert programmer. And so, we can do this pretty simply in torchtune, set up a new data set with a new source, and and this is related to, the model's not changing, the optimizer states aren't changing. What's changing is the sort of activation memory that is needed here. Since we are storing much longer sequence lengths, it takes up more memory in those intermediate tensors, and it pushes us out of bounds of the 40 gigabytes, and we're screwed. So what can we do? We can just keep swimming. There's more levers that we can pull. We talked about 8-bit Atom. We can just go down to 4-bit Atom W. So using even less. I mentioned QN2 1.5 billion or 0.5 billion, so smaller models. And we just keep going along this route. We keep throwing a smaller model at it, smaller optimizer, activation checkpointing, gradient accumulation, and we just hope and pray that it fits in 40 gigabytes. And this is a valid approach, and it works decently well depending on your task. But we can also change the paradigm completely. So I don't think this is an unfamiliar phrase to most of you. LoRa, so low rank approximation. Uh, so this whole time, what we've been doing is sort of taking pre-trained weights and doing a full update on those weights to get this new model. Uh, but instead, what we could do is we can freeze our pre-trained model, and instead of updating all the weights, we instead update matrices that approximate the weights. Again, very hand wavy explanation. There's a lot of great resources to sort of go deeper into this. And what that means is that you have a much smaller number of parameters that you have to update, which means everything just shrinks. So your optimizer states shrink because it's not the number of params for the original model needed; it's the number of params for your matrices that are approximating the model. Because that's smaller as well, your gradients and your activations shrink. So we've taken our pretty standard model here, our understanding of what goes into this, and we've shrunk everything. And I've got a picture of that too. Yeah, like this. So LoRa weights, there is a way you can exactly sort of quantify this. Good rule of thumb is usually between 1%, 2% of the full model. Now we can actually use, if we want, we can use a pretty standard atom W instead of the 8-bit atom, since it's only for the lower parameters. Activation smaller, gradient smaller, like I said, everything fits. So we LoRafied it, we did an approximation, and now we can train our 7 billion model. In torchtune, pretty easy to sort of set this up. Real quick, you can sort of LoRafy different modules within a model. So approximate different aspects of a transformer, essentially. So in the attention, the Q projection or the V projection, so the query or the value. You can also apply to the MLP on the output of that. The output, then the rank and the alpha, these are going to affect how big your matrices are. The rank is, the alpha is slightly different. But yeah, that's sort of how you do it in torchtune. And then we go to the logs and we see how we're doing. So this one over here, the peak memory allocated, that looks great. We're now under 20 gigabytes, and so we're not super worried about hitting that max memory limit. This over here is what looks slightly more concerning, right? So we, instead of seeing the sort of straight drop down and over where it appears to converge pretty quickly, we are slowly converging, and so it's true that in thinking about this, it's an approximation. We are not taking the full model weights and learning something and passing those updates throughout the entire model. Like it's instead learning to this much smaller matrix, and then at the end we can merge those back into the main model. But it's an approximation. It's not going to be out of the box just as good as full fine tuning. And so there's actually some interesting papers here talking, if any of you are familiar with Daniel Hahn from Unsloth, it's talking about how LoRa learns less, forgets less, is the sort of premise there. There's certain tasks where people have hypothesized that it generalizes better because it's this approximation, doesn't overfit to data. But at the end of the day, I think it's important to just remember that it's a tool. LoRa is a tool that if you're memory constrained, it's good to check out. these graphs are really nice to look at during training, but the sort of end source of truth is playing around with your model and running it through evals. And that's the only surefire way to understand if your model has been fine-tuned to your liking or whatever domain that you want. But this isn't all that we can do. We can QLORify it as well. So before I was talking about how 8-bit atom is quantized or approximates uh, you know the sort of storage of a 16-bit atom W. And we can do a sort of similar thing. We can quantize our original model so that, like, back to those first two levers, it's model size, optimizer state. With LoRa, we are attacking the optimizer state, I would say, like, plus everything else. We just need much less memory for everything there. But the model is still taking up 7 billion times 2 bytes parameter, 14 gigabytes. So we can attack that even further. We can quantize it down to standard is NF4 tensors. So divide it by roughly 4. And now our model is taking up 3.5 gigabytes instead of the 14 gigabytes. So we've just increased the amount of overhead that we have there. And yeah, so just keep swimming. What's the biggest model that we can possibly train in 40 gigabytes? So putting everything all together, we quantize the base. We use something like 4-bit atom W. We have activation checkpointing on. We have a batch size of 1 with gradient accumulation. And we can technically make 70 billion fit in 40 gigabytes. It's more of a toy example than anything. For the purposes of this, honestly, I think the 22 billion codestral is probably the one of the best models that you could try to fit in 40 gigabytes. I think it's a good lesson of just because you can doesn't mean you should. Trying to quantize everything down, it's a balancing act. Once you get into applying all these tricks, like I said, it's back to the evals of what's actually going to work best. There's good rules of thumbs, but the end judge is you and your evals. So I don't know. I've sort of the way I sort of previewed this talk on Twitter was that it was me word vomiting about all the things that I deal with in my day-to-day life for roughly an hour, which I think I've held true to. This is anytime I'm fine-tuning a model, these are the things that I actually consider. If I want to get like the absolute best output, I'm thinking about what's the best model that I can use as the base, as my starting point, the optimizer, how much gradient accumulation should I use? Do I need to checkpoint the activations? Okay, then my model is going to be a little bit slower on training. Is that okay? All of the random thoughts that are going through my head. And so we talked about those. We talked about using smaller models, quantizing the optimizer, simulating global batch size, and at the very end, changing the paradigm completely. Throw out this old school full fine tuning. We use LoRa, we use QLoRA, call it a day. Right. So am I going to have the best model ever now? I spent most of this talk talking about just trying to get things to fit in 40 gigabytes. But this is very it's a important thing, but it's not the most important part. Most important part is this data. So this is where I live a lot of time. This is the Hugging Face Hub datasets page. So I often find myself just going through and finding what cool datasets that are out there. There's I think Clem, the guy who is most prolific on Twitter from Hugging Face, one of the founders. tweeted something like there's hundreds or thousands of new data sets and models a day on the Hugging Face Hub. And so just coming here, checking, seeing what's trending. You can filter by code. You can do a full text search if you want like specific code or logic problems. It's a great place to start. I actually think I see in this screenshot something from the SWE agent team talking about SWE bench. So that would be a good place to start as well. And also in torchtune, it's pretty easy just to combine as many data sets as you could possibly want in your config, or you can make custom data sets. It's pretty easy. Yeah, there's even more. So I felt obligated to talk about this. We had Vincent on last week, I believe, from the TorchRL team, and he briefly talked about the reinforcement learning from human feedback, a very sort of basic form of reinforcement learning, but to sort of hammer home this point that the data is the most important tool that you possibly have to making your model better. So if it's the most important part, then you need to have the best data. And so what RLHF can do is that it can sort of use humans as the sort of ground truth for what is good data and what is not good data, and train a reward model, optimize your policy. And this is sort of just an overview of PPO. One of the sort of really awesome things I like about torchtune is that we have these recipes here. These are the Python file names, but because it's just very clear, very hackable, we actually had 2 contributors to the library just take a look at this and pretty easily implement both the PPO, and so the proximal preference optimization, and then the direct preference optimization for single device. So they were able to just take a look at the training loop, put in the losses that they wanted, and there you go. You have RLHF in torchtune. So I encourage you to take a look at these as well. For DPO, it requires a little more memory. I'm not sure it would fit into 40 gigabytes, but check them out regardless. There's, like I said, it's all about the data. This is a way to ensure that you have really great data. Also more, keeping on with the train of just word vomiting, important information that I think about every day. So I mentioned a little bit earlier that when you're doing these memory optimizations, a lot of the time it comes at the cost of performance. And so there's another handful of tricks to sort of speed up that performance. So for most of us, we're training on GPUs, most likely backed by NVIDIA CUDA. And there's ways in which certain parts of a transformer model can be combined into what we would call like a kernel. So all of the steps sort of happen in the same sort of piece of memory, and this speeds things up. I mentioned also briefly earlier, there was about Daniel Hahn from Unsloth, who is just an insane character, who for the most part handwrites these kernels to insert into different models, different architectures at certain points, to show huge performance improvements. PyTorch is taking a sort of higher level approach where they want to enable this not on the sort of individual model level, but rather try to leverage a compiler to identify these pieces of an architecture that can be fused together for potential speedups. And so I encourage you to check out both sort of projects. Compile is definitely a bit of a longer play, but Unsloth is very impressive, and they actually show that you can do some pretty amazing training in like a Google Colab notebook like T4 with 16 gigabytes of VRAM, which again is overkill for this sort of competition. Um, but maybe you want to check out trying to like fit a slightly bigger model with some of their kernels that might give you some better performance when you're going through. Because you, like Thomas said, you only have 24 hours to do your whole sort of training and inference run here. So worth checking out. Another thing would be sample pack. And I wish I had a good diagram here. You can sort of see where at a certain point, my slides get slightly more abstract in this presentation. But sample packing, the notion being that if we have a max model sequence length of 8,000, but we're using alpaca, or some of our samples aren't taking up a full 8,000 sequence length, we can fit more samples in each sort of fit pieces of a sample into what we consider like one single sample, add a mask to make sure that we do it properly, and we're sort of bluffing our sort of sample length. So we're getting on all of our samples, we're getting to 8K. We're not wasting any time. We can get through an entire data set usually much quicker. Showed like 2 times performance in torchtune. And so we have that implemented as well. It's easy to turn on with just a little Boolean. Real quick, wrapping up here, what's next for torchtune? We're looking at multimodal models. So obviously there's been a lot that have come out already. I think yesterday, even just Phi 3.5 came out with some vision capabilities. So we're really interested in how do we efficiently fine-tune multimodal models. It's, I think, a question that's very new. And so we're trying to do it in an efficient manner as well. We talked about, we're very conscious about memory and performance. And then when we introduce, vision capabilities, all of a sudden, so much more memory is needed. And so we're trying to figure out how to handle that. It's coming soon. Always interested in how we can tweak memory and performance, primarily focused up to 8 GPUs. But as models get bigger, we might consider some more. And then it all comes back to data. Data is the most important leverage you have to making your model better. And so we want to incorporate better data mixing utilities. Things like if we think this data set is going to be better, maybe we sample it twice as much as a different data set. Some things like that.
I just want to add that like the problems,
Yeah.
most of them have an image describing the task you need to solve for this hackathon. So
Yep.
yeah, maybe a multimodal
Yeah,
tool
that's
is going to be more
it's
capable.
mhm.
Us as
That's
humans
a
like
good point.
benefit greatly from that diagram to understand what is asked
Mhm.
to solve. So
Yeah, that's a good point. It's I went through and I worked with some of the sample problems from Hacker Cup, and just using text capabilities. And it was possible to get some of them, but I'm sure having the image would be much more helpful. And so that'll be something sort of available in torchtune soon. But you're right. It was even like looking at the dim sum problem in particular. I was reading through that made very little sense to me, and then I pulled up sort of the images, and I was like, okay, so you can move down and over. But if you move down to that road, then you can't go. That's the end of your move. So yeah, if it helps me, it would help a model too. Yeah, we've got GitHub, Discord. Always happy to chat. Open an issue if something doesn't work, or if you want to see some new features. Yeah, we're online most of the time, and very eager to talk about all things fine tuning. And you could even maybe get us distracted in talking about pre-training or multimodal models or literally anything under the sun. Yeah. Some special thanks to Mark Seraphim, Jane Shu, Wing from Axolotl, whole torchtune team, and Weights and Biases. I'll leave this slide up here, but
I can vouch for
yeah,
that.
sorry, I
I've
just
been
ranted for
lurking.
so long.
No, don't worry. Like we don't have questions. I don't see anything on YouTube or maybe the Discord that we have for the Hacker Cup. But I want just to chat a little bit about like how will you tackle the problem of fine tuning for this competition? Of course, you need a data set, but we have all the past
Mhm.
10 years or so problems. But probably that's not enough. Um, if you put everything together, you will need some formatting to create kind of
Yeah.
instructions. And I feel that at least for the smaller models, you will not shouldn't shouldn't try to one shot them. Like you should create a capable reasoning model that you can interact multiple times and then maybe produce
Mhm.
multiple solutions and then pick the best one or something like that. So
Yeah,
yeah,
absolutely. The yeah, I think, the throwing, as much good quality data with some instructions, uh, is a great first step. Um, I would try. I think my advice would be to use as much of the 24 hours to train on data as possible. Using 405B to generate synthetic data is a super interesting idea. I think you guys had already sort of mentioned that. Um, but yeah, doing this in one shot, I think is an incredibly hard problem. I think, passing multiple messages, getting, it's speed running back to the beginning of this talk, right? Like um, it's this sort of giant cloud that is an AI system, and somewhere in there is a model, but that's not the only piece, and it's not a one shot model or a zero shot model. It's building up some reasoning. I think you actually link some logic data sets, which is I think super helpful. Uh, Giving the data set some more instruction of like how to think through this logically, not just output some random code. Uh,
yeah.
yeah, that's a good point.
I think I would tackle this in a way that I will take one of the big models, maybe proprietary or not, and
Mhm,
then kind of steer it to find good solutions, actually solutions that pass, kind of trajectories that end up
mhm,
generating something that's a solution for the previous year problems or another, yeah, and mixing that with other data sets. It probably
mhm.
requires some manually or automatic. You can automatically select because you can verify the solution if it is correct, but and
Yeah,
then like those will be like conversations like with multiple turns probably to end up,
yeah,
and those would be your samples to like people tend to think that instruction tuning is just like input output, but it could be like a set of turns, and most of these models right now
yep,
support like llama 8b or Mistral. They all support like multi-turn conversations. Of course that will
mhm,
be longer context, and depending on the maximum context, um, yeah, because there's like maximum potential inference context and like maximum training length, and they're like
yeah,
different, like going, yeah, up to more than 8 or 16K. I think it's going to be hard with 1 GPU on basically any capable model. So you'll need to
yeah,
really cut the conversations at some point. Yeah,
yeah.
it's not easy.
The
Like
yeah,
creating
'cause
a data set that with this constraint, it's not easy creating a good data set that
So, for a lot of the large pre-training, we talk a lot about, these large language models as sort of the core of this. Um, but there's a lot of other great, much lighter weight, sort of understanding models. The BERT came out in 2018, 2019, and is still like the variations of BERT are really great for just semantic understanding. I think the Llama team, when they were collecting data, had trained just a Roberta model, I think. Don't quote me on that, but a variation of BERT model. So super lightweight to sort of classify like, is this good data? Is this bad data? Um, and like I would encourage like potentially an approach like that where you're, like you said, it generates some outputs. You can automatically verify that it at least works on the samples, and then maybe you have another sort of layer of BERT maybe classifying like, I think this is good, I think this is not, or you could throw another large language model at it. There's lots of ways to go about this problem.
Yeah. And then like, yeah, of course, as you said, like train as much as possible, like 23 hours of training and like
Mhm.
1 hour of eval. And
Yeah, yeah.
and I think how big can we train? I think 1 billion tokens or is around that you should be able to do on with the largest possible model. That's going to be like a 12B or something like that.
Mhm. Yeah, yeah, around there.
Maybe a little bit more. I don't know. Like, yeah, you need to, you put like quantize more.
Yeah, there's lots of levers to pull to, and it just test out a bunch of different things, and then the script you put together is a really great starting point for, it goes through those sample questions, and you see how your model does, but then
Yeah.
just chatting with it, giving it a bunch of example problems, and maybe even you can try evaluating it on, there's a bunch of code related eval tasks that are available through like the Luther AI eval harness, which is also integrated with torchtune, um, to give you a feel. But obviously, it's not the same exact uh, sort of format as like, this is the Hacker Cup leak code esque question, and this is the code that you want.
Yeah. I think having like a good evaluation pipeline that it's easy to use and so you can like iterate fast. So maybe you
Hmm.
will start like training 1 hour and then like, yeah, ideally you should probably have like a multi GPU machine to iterate faster because yeah, some of the fine tunes could take like 20 minutes on a big machine. And then
Yeah,
yeah, iterate, like run your eval. Okay, I got like 1 out of 20 problems correct.
yeah,
Or and then like when you see improvement, like hey, that recipe may work, maybe train for 3 times more, rerun the benchmark. Oh, it's improving. Switch them all,
yeah,
base model, whatever. Um,
yeah. It's
yeah, I
a
think
it's an iterative process. Like, it's, there's lots of rules of thumb to sort of get pointed in the right direction, but then it's you're trying things out and experimenting. Weights and biases makes it really easy to sort of log, your speed, how much memory you're using, your loss, and even I think some eval numbers too, if you wanted. Um, Luther eval harness has a lot of good data there too.
yeah,
Um,
yeah, I think we have an integration with eval harness also, so you can log your eval harness detailed results with the actual samples. I don't know if
mm,
you could implement like an eval harness for this competition. You'll have to write the competition kind of the correct format so it's supported. I feel it's maybe overkill.
yeah, I mean, they're pretty, maybe overkill. It depends on how much, like you said, you could hop on RunPod, rent out, a fleet of GPUs, and just launch a whole bunch of different training runs. And if that's your approach, then maybe it's worth
Yeah,
uh, doing an integration with the eval harness. I will say, Haley and Lingtong and that team are super responsive to GitHub
yeah,
issues and on Discord. So uh, asking for their help to put together like a little task format that fits
yeah.
their
But
kind
I
of
feel like
expected
at
input
least
is
at least from my point of view, and maybe you have shared the same as me, that probably you should spend like 99% of your time creating a data set and having a small feedback loop where you fine tune and try to see if your data is actually good. Like creating
Yep.
a high quality data set, and you can could do some math kidnap, like, hey, if I'm going to train, I don't know, like a 12b to 24 hours, I need X amount of tokens. And that's my like maximum
Hmm.
budget. So like once your data set has that amount of tokens, then you have to refine it and just filter out the best answers. And then maybe, yeah, then like you have like a V0, V1, V2. Um, the fine tuning is, as you, the torch tune is extremely easy. So basically, once you have put your data set on the good JSON L format that torch tune expects, or Axolotl or whatever, then it's like hitting
Hmm.
run and just, and I don't think like fiddling with the hyperparameters, besides what you explain about like fitting them all into the memory, so
Yeah.
yeah, a little impact, like maybe targeting all the layers or the lineals or like just the head or whatever, that may have some impact.
Hmm.
But we're not training that long either, so I don't know. Yeah, maybe try to
Yeah.
with relearning
It's
rates, but don't
yeah.
spend
The
hours fiddling with that.
yeah the I feel like that used to be such a huge part of
Oh yeah.
trying to get out the best model was the sort of grid search, hyperparameter searching.
Oh yeah, yeah, we
Um,
love that.
but yeah, now I feel like I think I agree with you completely. It's the data. We can try. Um, there's a lot of great advice on which LoRa pieces
Yeah,
to target. Um, so trying out like some of those things, that's probably going to give you the best gains. But it's you know make the best possible data you can, find the best data sets, create the best data sets, share them with us. We love to see them.
yeah,
Uh,
yeah. No, it's actually, I think that's the big part, like creating a good data set. And you can even, like, if you don't want to spend GPU time, you could fine tune on one of the like services, one of the big malls, and then like that's your baseline.
mm,
Like that's probably, I will not get as good as that because that base mall is going to be bigger. Um,
mhm,
but I don't know. I often use like Mistral fine tunes, and there's like an endpoint with an API, and just like, yeah, it's like no
mhm,
code basically, or
yeah,
OpenAI or whatever, any of like the providers. And then you have them all
yeah,
served for you on an address, and then like you can use it straight away. Because like even if you fine
right,
tune now, then you have to serve them all. So you will need to learn a little bit
right,
like on maybe VLLM, you host that on Docker image, and like hitting that endpoint to get the, because then you need to run your yeah, the solutions as fast as you can, on ideally on a sync, so that you can run them in parallel. And probably, as we were
yeah,
saying, like it's not going to be a one shot, it's going to be like multiple interactions for every single problem. um,
mhm. Yeah, and I think for
so
each problem, it's time box to 3 minutes for open track. Is that right?
6, I think. No,
Six? Could be
yeah,
wrong.
no, yeah.
Um,
So that
not
limits
a
the number
ton
of
of time.
interactions you can make with them all.
Say again?
So that would limit actually the number of interactions that you can. If you're doing agentic and the agent
Yeah.
is very heavy and it's gonna call 2,000
Mhm.
times, it's gonna like, you're gonna run out of time. Um,
Yeah, yeah. Then you have output nothing.
and you have output nothing basically. Yeah, yeah. Thank you very much for
Um,
having for coming here. And I think people will end up asking when we are closer to the date and people actually start fine tuning stuff.
yeah, no, it's lovely to chat with you. It's I think I tried to cover. This is the memory is the big limit. You got to try to fit the best you can, and best model you can with all these like other tricks, and then just throw some really great data at it, and do some turns and see what you can find out. So, you there?
I got kicked out.
That's